All right, hi, this is Matt Dean with A Plus College Ready, and now we're going to work some momentum practice problems. So practice problem 1, we have a box sliding across a horizontal frictionless surface to the right with a speed of v, positive v. At time 0, a pushing force is applied toward the right on the box. The graph included on the right displays the applied force graphed against time. Which of the following describes the box's change in momentum between t equals 0 and t equals 6? So we're looking for the change in momentum, delta P. Remember, that's equal to m delta V. We also should know that the change in momentum is equal to the impulse, J. Well, impulse is equal to force times change in time. So m delta V equals F delta T. Well, over here we have a force versus time graph. Remember that the area under the curve of a force versus time graph is equal to impulse. So let's find the impulse. Now our shape here is essentially a trapezoid. To find the area of a trapezoid, we say A equals 1/2 base 1 plus base 2 over height. So the bases are the lengths of the bases. So down here, this base has a length of 6, and up here, this base has a length of 2. So we're going to say A equals 1/2 6 plus 2 times the height. Well, the height, we don't have any units on our y-axis. Our height is just F max. So if we simplify a bit, 1/2 times 6 plus 2, so that's 1/2 times 8, that's 4. So our area is 4F max. That area is equal to our impulse, J. And remember that impulse is also equal to change in momentum. So our answer here is that the change in momentum is equal to the impulse. And the impulse is positive 4F max. The box is moving to the right. It had a positive velocity. This is going to increase it and make it even a bigger positive number. So our answer is the momentum of the box increased, and it's going to increase by essentially 4 times F max. So we're looking at answer B. Problem 2, we have a 4 kilogram box sliding across a frictionless horizontal surface with a velocity of 5 meters per second. And it collides with and sticks to a 6 kilogram object that was initially at rest. What is the resulting speed of the objects after the collision? Well, this is an inelastic collision. We're going to have to apply the conservation of momentum to make this work. So we're going to do something like this. M1 V1 plus M2 V2 equals M1 V1 prime plus M2 V2 prime. Well, the mass of our first object, we'll say is 4. The velocity, the initial velocity of that object was 5 meters per second. So that's M1 V1 plus M2, which is 6. Its initial speed, though, was at rest, so its initial speed is 0. So this whole M2 V2 term becomes 0. That's equal to M1 V1 plus M2 V2. Now here's something that we need to look at. This is an inelastic collision. That means that our two objects stick together. So instead of writing them out separate, let's take this mass and add it to this mass, because they're going to be together after the collision. So we're going to say that's equal to M1 plus M2 times some velocity. We'll just call it V1 prime. So here we're going to say that's equal to 10 kilograms times V1. We're going to multiply 4 kilograms times 5 meters per second, get 20 kilogram meters per second. We're going to divide both sides by 10 kilograms. And we're going to end up with a final velocity, V1 prime, of 2 meters per second. So the combined objects are going to continue to move toward the right at 2 meters per second. All right, looks like the same problem, but this time we're looking at what is the total change, what is the change in total kinetic energy after the collision. First of all, we need to know what's the kinetic energy before the collision. Remember that kinetic energy is 1/2 mv squared. So before the collision, we've got 1/2 times 4 kilograms times the velocity squared. So it's 5 meters per second. That's all squared. So 5 squared is 25 times 4 is 100 times a half is 50. Remember, this is energy, so we're talking about 50 joules. The 6 kilogram object doesn't have any kinetic energy because it has a velocity of 0. So this is the kinetic energy before the collision. Kinetic energy after the collision, let's calculate it up top. That's going to be equal to 1/2. Remember, our two objects are combined together, so they have a mass of 10 kilograms. And we calculated in the last problem that the velocity of the combined objects was 2 meters per second. And that's got to be squared, mv squared. So we calculate that out. So 2 squared is 4. 4 times 10, 40 times a half is 20. So our kinetic energy after the collision, 20 joules. To find the change in kinetic energy, the change in anything, is going to be the final minus the initial. So in our problem, our final kinetic energy was 20 joules, minus our initial kinetic energy of 50 joules. So we end up with a change in kinetic energy of negative 30 joules. So we're looking at answer C as the correct answer. All right, now we're working on momentum question 4. In this one, an object has a mass of m and a speed of v and moves horizontally and to the right and collides with a stationary object 2 of mass 4m. Assume the collision is perfectly elastic. What are the velocities of the objects following the collision? So this is a problem where we're going to have one-dimensional collision, but we're going to have two unknowns. So that makes this one a little bit more difficult. So we're going to go over to the next slide to work this one out so that we have some space. First of all, momentum is conserved. So we're going to set up a conservation of momentum equation. And we're going to say m1 v1 plus m2 v2. So that's the momentum before the initial momentum of both objects is equal to m1 v1 prime plus m2 v2 prime. So this is the momentum before and the momentum after the collision. Now let's plug in what we know. The mass of the first object was just m, and the initial velocity of the first object was just v, plus the mass of the second object was 4 times m, and its velocity was 0. That's equal to the mass of that first object times its final velocity, which we don't know, plus the mass of the second object, 4m, times its final velocity, which we also don't know. All right, we can simplify out this term since there's no initial velocity there for that one, so let's just erase that. We don't need that term. And that leaves us with this equation so far. Now we can solve this for either v1 prime or v2 prime. I'm going to solve it for v1 prime. So I'm going to subtract negative 4 mv2 prime from both sides. I'm going to divide both sides by the mass, by m. And what that gives me is v1 prime is going to be equal to v, the original velocity, minus 4 times v2 prime. All right, so that's an important equation. Now I need to go back to the equation that I derived from the law of conservation of energy, and also from the law of conservation of momentum in the introduction to momentum video. And that equation was v1 plus v1 prime equals v2 plus v2 prime. This is an important equation, and it'll help you work these one-dimensional collision problems with two unknown problems much easier. So now what we're going to do is we're going to take this that we derived from the momentum equation, and we're going to substitute it in to this equation for v1. So when we do that, our initial velocity, instead of writing, or for v1 prime rather, instead of writing v1, our initial velocity of our first object was v. For v1 prime, we're going to substitute this. So that's going to be plus v minus 4 v2 prime equals v2. And remember, v2, that's the initial velocity of the second object. That was 0. So we don't even need that term. Plus v2 prime. Now we're going to combine our like terms. And when we do that, the easiest way to do that would be to add together the two v's here to get 2v. We'll add the 4v2 prime to both sides. And then we'll divide both sides by 5. So that gives us v2 prime equals 2/5 v. Now, we can take that and we can substitute it in. The easiest place to substitute it in for would be to substitute it into this equation. So when we substitute it into this equation, we end up with v1 prime equals v minus 4 times 2/5 v. We solve that for v1 prime, and v1 prime is equal to negative 3/5 times the original velocity. So that's one of our answers. That's the velocity of the first object after the collision. Now we also need to know the velocity of the second object after the collision. We can find that in, well actually we already got that. We've got that right here. So this is the object of the first velocity after the collision, and 2/5 times v is the velocity of the second object after the collision. All right, let's move on to the next problem. All right, so now we're moving on to momentum question 5. Two blocks of masses 4m and 6m respectively initially travel at the same speed v but in opposite directions. The 4m mass travels in the positive direction while the 6m mass travels in the negative direction. They collide and stick together. What is their velocity after the collision? Give your answers in terms of the original velocity v. So, what we've got to do here is this is another inelastic collision. So we know in that case we're going to say that mass of the first object times the speed of that object, which was positive v, plus mass of the second object, 6m, times its velocity, which was negative v, equals, remember these two things are colliding and sticking together, so the total mass is going to be 10m times their new velocity, which we'll just call x. So now we want to solve this out for x. So let's simplify. So over here on the left we have 4mv plus, this is going to end up being negative 6mv. So when we combine those, on the left we get negative 2m times v equals 10m times x. We want to divide both sides by 10m. Notice the m's cancel. We get negative 2/10 times v is equal to x. X is what we're looking for, the final velocity of the combined masses. We could simplify that fraction or reduce it down and get negative 1/5 v is equal to the final velocity of our combined masses. So we're looking on number 5 at answer C is our correct answer. So now let's move on to number 6. Number 6 again looks like the same problem, but this time we want to find how much kinetic energy is lost to other forms of energy. We want to give our answer in terms of m and v. So first of all, we need to calculate the kinetic energy before the collision. So that's going to be equal to 1/2 mass of the first object times the velocity of that object squared. So that's going to end up being 2mv squared. We also need the kinetic energy of that other object, so this will be 1/2 6m times negative v squared. So the negative doesn't matter here because it's going to square out. So that's going to end up being 3mv squared. So our kinetic energy before the collision is going to be the sum of these two. I'm going to call that KMI, initial kinetic energy, and that's going to be 5mv squared. Well, our kinetic energy after the collision is going to be 1/2 times the combined masses of 10m times that new velocity, which was -1/5 v squared. So if we do the math here, let's square -1/5, that'll be 1/25 times 10, so it's 10/25, times 1/2, which is going to make it 5/25, or 1/5 mv squared. So we started off, and remember 1/5 is the same as 0.2, right? So we can think of this as 0.2 mv squared. That's the final kinetic energy. We started with 5 mv squared initially. We ended with 0.2 mv squared, which means we lost 4.8 mv squared worth of energy. So this doesn't ask for the change in, this just asks for how much was lost. So we could take this answer as just positive 4.8 mv squared. Let's move on to number 7. This time we have a tennis ball moving to the right at 42 meters per second. It collides with the wall and bounces off toward the left at 38 meters per second. What is its change in velocity? Remember that the change in anything is equal to the final minus the initial. So in this problem, our final velocity is 38 meters per second to the left. Since it's to the left, we need to write that as negative. We want to subtract from that the initial velocity, which was 42 to the right. Well, that 42 needs to be positive, so minus positive 42 meters per second. So our change in velocity is going to be equal to negative 80 meters per second with the appropriate significant digits. Answer C looks good. Next problem again looks very similar, but this time we're looking for how much impulse acts on the object. Well, remember that impulse is equal to change in momentum. And remember that change in momentum is equal to m times change in velocity. Well, we know the mass of the ball. So the mass of the ball is 0.1 kilograms. We just calculated in the previous problem that the change in velocity was negative 80 meters per second. So if the product of those two, negative 80 times 0.1, is going to be equal to the change in momentum, which is also equal to the impulse. So when we do the math, 0.1 times negative 80 comes out to be negative 8. With 3 sig figs, we're going to write it as negative 8.00. And the units are going to be kilogram meters per second, which are equivalent to newtons times seconds. So that's our answer on problem number 8. And that is answer D. Alright, again, this looks like a very similar problem. Same tennis ball, colliding the same way. But this time, if the ball was, this should say, was in contact with the wall for 0.05 seconds, what average force was applied to the ball by the wall? Now remember, when we're thinking about forces and momentum, we need to think about F delta T equals M delta V. And remember that M delta V is equal to J. It's also equal to delta P. In the previous problem, we found that the impulse was negative 8 Newton seconds. So we could say that negative 8 Newton seconds impulse is equal to F delta T. So if we go a little closer here, we're looking for the force. They give us the time. The time that the force is applied is 0.05 seconds. So we're going to divide both sides by 0.05 seconds. Seconds cancel. And if we go negative 8 divided by 0.05, we end up with negative 160 newtons. So with 3 sig figs, our correct answer is going to be B. Alright, so here's problem 10. So this time we have a tennis ball, 0.0750 kilograms, moving to the left at 8 meters per second. It's hit by a racket, which is moving toward the right. The graph on the left displays the force applied to the ball by the racket as a function of time. What impulse acts on the ball? So this is a force-time graph. We know that the area under this curve is equal to impulse, or change in momentum. So we just need to find the area under the curve. Well, this is a triangle, and we know to find the area of a triangle, we're going to use 1/2 base times height. So the base here has a length of 0.5, and that's seconds. And the height is about 150 newtons. So if we go 150 times 0.5 times 1/2, we end up with an impulse here of 37.5 newtons times seconds. And notice that's a positive number, because even though the ball is moving to the left, the force is pushing it toward the right. We get a positive force, a positive impulse in this case, and a positive change in momentum. All right, this problem 11 again looks like the same kind of ball, but this time it says the graph displays the force applied by the racket. What is the ball's change in momentum? Well, in the last problem we found the impulse, J. We know J is equal to change in momentum. So there's no work really to do here. The area under a force-time graph is both impulse and change in momentum. We found that in the last problem to be 37.5. Problem 12, same situation. This time we want to know what's the ball's change in velocity. Well, we know that its change in momentum was 37.5. We know that change in momentum is equal to mass times change in velocity. So what we could do is say 37.5 equals to the mass of the ball times the change in velocity. We're going to divide both sides by 0.075. Alright, so once we divide by 0.075 kilograms, this all cancels. The kilograms over here cancel. 37.5 divided by 0.075 gives us 500 meters per second. And again, that's positive 500 meters per second. The velocity is changing very quickly in the positive direction. Next question. A boy holding a medicine ball slides across an icy parking lot. The boy throws the medicine ball forward as the sled slides across the parking lot. So let's say this is the sled. You got a boy up here. And the boy throws a heavy ball, a medicine ball, the same way in which he's moving. Which of the following correctly describes the velocity of the center of mass of the sled boy medicine ball system just as the medicine ball was thrown? Assume that no friction or air resistance acts on any part of the system. So this is a closed or isolated system. And we talked on our intro to momentum screencast that in closed or isolated systems, momentum is conserved. What that should tell you is that the velocity of the center of mass doesn't change before or after the collision, or in this case, the throw. So what we're going to say is that the momentum of the center of mass, or at least the velocity of the center of mass after he throws the ball, is the same as the velocity at the beginning of the problem. The velocity at the beginning of the problem was not the velocity of the skater, it was the velocity of the boy and sled together. So the answer should be D with some minor modifications. The velocity of the center of mass after the interaction, in this case the throwing of the ball, is equal to the velocity of the center of mass at the beginning of the problem. And that's because momentum is conserved. The mass of the system doesn't change. That mass is just spread out further when the boy throws the ball. Here's problem 14. The graph displays the position as a function of time for the center of mass of a system of particles with a total mass of 8 kilograms. At approximately 10 seconds, a short external force is applied to a particle in the system. What is the change in momentum of the system? Well, remember that change in momentum is equal to m delta v. It's also equal to F delta t, or J, impulse. Now, in a lot of these problems, we're going to be given force versus time graphs. But notice here, we're given position versus time, not force versus time. So hopefully you remember from our first unit in this course that position time graphs, something easy to glean from a position time graph is velocity. The average velocity is equal to the slope of the line between 2 points. So we could find the slope of this line between the initial point and right here. And that would be the initial velocity of our object. So if we find the slope here, we'll say slope equals the y at 10 seconds looks like it's 15. So 15 minus the y at 0, which is 5, over change in x, well, 10 minus 0. So when we get that slope, that's going to be 10 on top, 10 on the bottom. Slope's going to be 1. So the initial velocity is 1 meter per second. We also want to find the velocity in this section of the graph. So again, we'll find slope. At 20 seconds, our y-coordinate is 10. At 10 seconds, our y-coordinate is 15, so we're going to go change in y. 10 minus 15 over change in x, 20 minus 10. So that's going to be negative 5 on top, 10 on bottom. So it's going to be negative 0.5 is going to be our speed during this section. Now we're trying to find change in momentum. Well, before we find change in momentum, let's find change in velocity. And to find the change in the velocity, we know the change in anything is equal to the final velocity, which in this case is negative 0.5 meters per second, minus the initial velocity, which in this case is 1 meter per second. So our change in velocity is negative 1.5 meters per second. Let's change in v. Now be careful and don't mark negative 1.5 as your answer, because we're not looking for change in velocity, we're looking for change in momentum. To find in change in momentum, we need to take mass times change in velocity. So our mass in this problem is 8 kilograms. We're going to multiply that by our change in velocity, and we're going to end up with negative 12 kilogram meters per second. So our answer on 14, C. All right, here's problem 15. A 20 kilogram monkey runs at speed v, grabs a rope that hangs vertically from the ceiling, and swings to a maximum height of 3 meters. Later, a 35 kilogram monkey, also running with a speed v, grabs the same rope and swings. What maximum height will the 35 kilogram monkey reach? What you got to realize is in the beginning of this problem, the first monkey has kinetic energy. He grabs the rope and begins to swing upward, and that energy that he has is converted to gravitational potential energy, mgh. What I want you to notice, assuming that the energy conversion is perfect and that none is lost, notice that these masses cancel out. So we could solve for h here, and we could say that h is equal to 1/2 v squared over g. Notice that the mass of the monkey doesn't factor in here. What determines how high that monkey goes is his speed and the acceleration due to gravity. Well, this is dependent on the planet you're on, and both monkeys start off with the same speed, which should tell you they will both swing up to the same height. So our answer here, 3 meters. Answer D. So problem number 16 is much like a problem we did earlier, problem number 4. It's another one-dimensional collision problem. We're going to have two unknowns in this problem. So again, that makes it a little bit more difficult to solve. So in this problem, we have a particle of mass 4 kilograms moving with a velocity of 2 meters per second. Collides elastically with a particle of mass 6 kilograms, initially moving with a velocity of negative 4 meters per second. What are the velocities of the two particles after the collision? So to make some space, we're going to move over to the next slide. And we're going to set up the law of conservation of momentum, which remember is m1 v1 plus m2 v2, the momentum before the collision, equals m1 v1 prime plus m2 v2 prime. So that's the momentum after the collision. In this case, our initial mass of our first object was 4. And I'm going to work this without the units just to make it less confusing. Typically, I would tell you to put the units in, but with these problems, there's going to be so many units, it gets a little bit confusing. The initial velocity of that first object was 2 meters per second, plus the second object has a mass of 6 kilograms, and it was moving at negative 4 meters per second. That's equal to the momentum after the collision. Well, the first object again had a mass of 4, and we don't know that final velocity. The second mass had an object of 6, and again we don't know its final velocity. So let's simplify this down a bit. So 4 times 2 is going to give us 8. 6 times negative 4 is going to give us negative 24. So that's going to end up giving us negative 16 equals 4 times v1 prime plus 6 times v2 prime. We could solve that for either v1 prime or v2 prime. I'm going to solve for v1 prime. So all I need to do is subtract the 6 v2 prime from both sides and then divide both sides by 4. And that ends up giving me v1 prime is equal to negative 4 minus 1.5 times v2 prime. That's going to be really important here in a second. Now we're going to go back and use the equation that we derived in the Introduction to Momentum screencast. v1 plus v1 prime equals v2 plus v2 prime. We're going to use this equation, and we're going to substitute this in for v1 prime into this equation. So when we do that, here's what we've got. We're also going to substitute in our numbers. So our velocity of our original object was 2 plus v1 prime, which we're going to substitute in, minus 4 minus 1.5 v2 prime. And that's equal to v2, which was negative 4. It's our original velocity of the second object, plus v2 prime. So now we're down to one unknown. So let's combine like terms. Let's add this 4 to both sides. So these 4s are going to cancel out. And then let's add this 1.5 v2 prime to both sides. So that ends up giving us 2 is equal to 2.5 v2 prime. We want to solve for v2 prime. And we end up getting 0.8. So v2 prime equals 0.8 meters per second. And that's positive 0.8. Now we can take that v2 prime and plug it into any of our equations up top. The easiest one would be this one. And we can solve for v1 prime. So v1 prime is going to be equal to negative 4 minus 1.5 times 0.8. Solve that down, and we end up with a v1 prime answer of negative 5.2 meters per second. So this is our final velocity of object 1, and this is our final velocity of object 2. If we go back to the actual problem, it looks like our final answer here was D. All right, question 17 is a ballistic pendulum problem. A ballistic pendulum is a device for measuring the velocity of a projectile, usually a bullet. It consists of a large, heavy wooden block suspended by cords, and that acts as a pendulum bob. A bullet is fired into the bob, and its momentum is transferred to the bob. The bullet and the bob collide in an inelastic collision. The bullet stays inside the bob after the collision. The momentum can be determined from the amplitude of the pendulum swing. The velocity of the bullet can be derived from that momentum. So in this case, we have a bullet of mass 0.12 kilograms fired with a velocity of 300 meters per second into a bob of mass 8.5 kilograms. What is the velocity of the bullet bob system just after impact? So this is an inelastic collision. We've got to use conservation of momentum. So the momentum before the collision is going to be equal to the momentum of the bullet. So the momentum of the bullet is 0.120 kilograms of mass times the velocity of the bullet. The bob initially doesn't have any momentum, so this is our momentum initial, and that's equal to the final momentum, which is going to be equal to the combined mass of the bullet and the bob, so that's going to be 8.62 kilograms times some speed, which we don't know. So we'll divide both sides by 8.62 kilograms, and we'll end up with a final velocity of about 4.18 meters per second. So that is the velocity of the bullet bob system right after the collision between the two. In this kind of inelastic collision, remember, momentum is conserved, but kinetic energy is not. A lot of the kinetic energy of that bullet is converted to heat and sound and other forms of energy. Let's move on to problem 18. Problem 18 is also a ballistic pendulum problem. Same setup. This time we want to know to what maximum height will the bullet bob system rise just after the impact. So here's the deal. The bullet hits the bob. A lot of the kinetic energy is converted to heat, sound, and so on. But the bullet bob system still has some kinetic energy. After that collision, the kinetic energy here, as the bob swings, is converted to gravitational potential energy. We're going to assume that from that point on, all of the kinetic energy that's left is converted to gravitational potential energy. So first of all, we need to know how much kinetic energy was there at that point. And we'll calculate that using K equals 1/2 mass. So this is the mass of our bullet bob system, 8.62 kilograms, times the velocity that we just calculated squared. Do the math on that, and that gives us 75.3 joules. So we're assuming that that's how much kinetic energy the bob has at this point right here. And that as the bob swings, all of that kinetic energy is converted to gravitational potential energy here. So we're going to say that 75.3 joules is equal to mgh, the formula for gravitational potential energy. So that's going to be 75.3 equals the mass, so that's 8.62 kilograms, the mass of our whole system, times g, 9.8 or 9.81 meters per second square, times h. We're going to divide through by 8.62 and 9.8 to get h, and we end up with h equals 0.891 meters. So our answer on this one is going to be B. And that height is the difference in height between here and here. So it's going to be this distance. So let's move on to problem 19. Same setup. This time we want to know what is the angle of the pendulum string with the vertical at the point at which the bob reaches its maximum height. So we want to know what's this angle right here. So the first thing we're going to do is we're going to draw a triangle from the center of our box over to the edge. The problem tells us that the length of our string here is 2 meters. We're going to call this distance x. And what we're going to do at this point is think about what we already know. We know the distance from here to here is the height that our box raised to, and that was 0.891. We know this whole distance is the length of the string, 2 meters, which means this distance x right here is going to be 2 minus 0.891. So that gives us 1.11 meters. So that's this distance here. So now we can use that and do a triangle essentially to figure out the angle. So we're going to say cosine of our angle theta, that's equal to the adjacent side of our triangle, which is x, 1.11, over the hypotenuse, which is 2. We'll divide 1.11 by 2. We'll take the inverse cosine, and we'll end up with an angle theta of about 56.3 degrees. So answer D is the correct answer on this one. This problem is a collision that occurs in more than one dimension. A hockey puck of mass 0.1 kilograms moves along horizontally and to the right at a speed of 5 meters per second. The puck collides with a glancing blow with a stationary puck, also of mass 0.1 kilograms. After the collision, the original puck moves off at an angle of 30 degrees to the left of the original horizontal direction at a speed of 2 meters per second. What is the velocity of the second puck after the collision? Alright, so first of all, we want to find the initial momentum of the system. And what we have is we have a 0.1 kilogram object moving toward the right at 5 meters per second. Well, that tells us, and the other object is stationary, which means our initial momentum of our system is 0.5 kilogram meters per second to the right. In this case, momentum is conserved, which means after the collision, this also has to be the final momentum. Or we might say this is the momentum of the center of mass of the system before the collision. It must also be the momentum of the center of the mass after the collision. So we collide. So here comes the first ball. It comes in and collides with the second ball, kind of in a glancing blow. The first ball, we'll call it ball A for right now, goes off in this direction. Here's the original direction. Second ball is going to go off somewhere in this direction probably. So we know that the first ball goes off in a direction 30 degrees to the left of our original direction. And what we want to know is what's the velocity of this second puck, of puck B. So the first thing we need to do is make a momentum vector diagram. Remember that momentum is conserved. Velocity is not. So let's make this top picture into a momentum vector diagram. So after the collision, the ball moved off with a speed of 2 meters per second at this 30-degree angle. That means its momentum after the collision was 2 times its mass, 0.2. So this vector here is 0.2 kilogram meters per second at that 30-degree angle. What we want to do is to break this into components. So we want to find the vertical component, we'll call that y, and we want to find the horizontal component, we'll call that x. And we'll just use trig to do that. So let's say sine 30 equals opposite side y over hypotenuse, 0.2. Do the math on that. So the sine of 30 is a half times 0.2. That gives us 0.1. So this is going to be 0.1. 0.1 toward the left. All right. Then we do the same thing with our horizontal component. We use cosine for that. Adjacent over hypotenuse is cosine. So we'll say the cosine of 30 times 0.2, and that gives us 0.173. This is 0.173. And that's going straight forward. Well, here's what we've got to think about. This other vector down at the bottom, vector B. The vertical component of this vector has to cancel out the vertical component of this top vector, because vertically our initial system didn't have any vertical momentum, which means our final system cannot have any vertical momentum. So the vertical component of ball B's momentum has to be 0.1 kilogram meters per second. This is also kilogram meters per second up here. All right, the final momentum has to be 0.5 kilogram meters per second to the right, because that was the initial momentum of the system. Well, ball A had 0.173 kilogram meters of momentum, which I hope tells you that the horizontal component of B had to be 0.5 minus 0.173. So that's going to be 0.327. So this is the horizontal component of ball B's momentum. This is the vertical component of ball B's momentum. So to get the total momentum, we can add those up using vector addition. So let's use Pythagorean theorem. And in this case, we'll say B squared equals 0.327 squared plus 0.1 squared. Solve for B. So 0.327 squared plus 0.1 squared. Take the square root of both sides and get 0.342. All right, so that's the magnitude of the momentum of ball B or puck B after the collision. We also need to know the angle, because remember, momentum is a vector, so you need a magnitude and direction. To find the angle, this angle right here, we'll just call it theta, and we'll say that let's just use tangent. Let's say the tangent of theta is equal to the opposite 0.1 over the adjacent 0.327. So go 0.1 divided by 0.327, take the inverse tangent, and get 17.0. So our final momentum of puck B, 0.342 kilogram meters per second at 17 degrees to the right of the original direction of puck A. Now, this problem didn't ask us for the final momentum of puck B. It asked us for the velocity. So since we have momentum, and we know that momentum is mass times velocity, we can simply divide the momentum by the mass to get the velocity. Well, our mass was 0.1 for puck B, so 0.342 divided by 0.1, that ends up giving us 34.2 meters per second. Remember, velocity is a vector, so we need to say 34.2 meters per second at 17.0 degrees to the right of the original direction. So if we look at our problem, our actual answer on this one is going to be, looks like we had a little rounding difference than what we had in the problem here, but it's A. Now let's move on and look at the free response questions. So in the free response questions, we have a 0.6 kilogram cart rolling with no friction along a straight horizontal table until it collides with a stationary 0.850 kilogram cart. So we might have a setup like so. So we have position time data for the 0.6 kilogram cart. And this should be in meters, not centimeters. So at t equals 2 seconds, the carts collide in a perfectly inelastic collision. And hopefully you know that means that they stick together. Momentum is conserved in that case, but kinetic energy is not. What is the velocity of the two carts immediately after the collision? So let's go over to the next slide and try to get a solution for this. All right, so here's what we're going to do. We're going to go to that table, and let's go back to the table for a second. So here's our table. We've got position time data. With position time data, hopefully you realize that if we thought of this as a graph, where we graphed position versus time, and we graphed our data, I think you'll see we're going to get a line like so if we graphed it out. We know that in a position time graph, the slope of the line gives us the velocity. So we want to use these points to calculate a slope. So I'm just going to say slope equals, remember it's change in y. We're going to graph position on the y. So I'll take the last y, 40, minus, I'll just take the first y, 0, over change in x, 2 minus 0. So 40 divided by 2, our slope is 20 meters per second. That's our initial velocity of cart A, or the 0.6 kilogram cart. Now, let's do a little erasing here. Make some space. So if we want to find the velocity of the two carts after the collision, we need to do conservation of momentum. And we're going to say the momentum before the collision is going to be the mass of cart 1, 0.6, kilograms. And again, I'm going to leave off the units just to make it clear here. Times the velocity of cart 1, 20. Remember that cart 2, the 0.85 kilogram, is stationary, so it has no momentum to begin with. So our initial momentum is just 0.6 times 20. That's equal to the final momentum. Now this is an inelastic collision, which means the two carts hit and stick together and move off as one object. So the total mass is going to be the combined mass, 0.6 plus 0.850. That's 1.45. And they're moving off at some velocity that we don't know. But again, this is momentum before equals momentum after the collision. Momentum is conserved. So we solve that out for x, which is our final velocity, and we end up with a final velocity of 8.28, positive 8.28 meters per second. So that's our answer to part A. Part B tells us the collision took place over 0.5 seconds. Draw and label a graph which depicts the velocities of both carts for the time interval between t equals 0 and t equals 4 seconds. And graph paper is provided on the next slide. So let's graph on this next slide. So first of all, let's graph the 0.6 kilogram cart. It was moving at a constant velocity of 20 meters per second, and it did that for the first 2 seconds. So let's see, let's make each one of these lines on the y-axis be 2 meters per second. So this is going to be velocity in meters per second. So let's say it's 2, 4, 6, 8, 10. It's going to be 10 right there. 12, 14, 16, 18, 20 right here. Alright, so the 0.6 kilogram cart for the first 2 seconds was going at a constant velocity of 20 meters per second. Something like that. Alright, then at 2 seconds, the collision happens. And it has a force applied to it. It starts to slow down. And it slows down throughout 0.5 seconds to the final velocity. And our final velocity, if we go back to the last problem, was 8.28. So between 2 seconds and 2.5 seconds, it's going to slow from 20 down to about 8.28. So if we look at our lines here, each one of these is going to be 0.25. So this is going to be 2.5 right here. And we want to go at 2.5. We want to be down at about 8.2 or so. So we want to get down to here, somewhere in this neighborhood. So let's just line like so. And then after that collision is over, the carts move off together at a constant velocity of 8.28. Since there's no friction, that velocity is not going to change. So essentially we should have a straight line, something like that. The other cart, we'll use a different color for that one, started off with a speed of 0, and it stayed that way for the first 2 seconds. And then between 2 and 2.5 seconds, it speeds up. It's accelerated, maybe something like that. And then after 2 seconds, it moves off with the other cart at a constant velocity. So that's our graph. That's our answer to part B. Part C says, what impulse acted on the 0.85 kilogram cart? Justify your reasoning. All right, so here's the deal with that. Now let's go to a blank space so we'll have a little room to work. We know that impulse, J, is equal to change in momentum, delta P. We could write that as F delta T equals M delta V. We know that original cart started off with a velocity of 0, and it ended up with a velocity of 8.28. So its change in velocity is going to be its final velocity minus its initial velocity. So its change in velocity is 8.28 meters per second. We can multiply change in velocity times mass to give us the change in momentum, which is also the impulse. So let's take 8.28 and let's multiply it by the mass of that cart, which was 0.850, to get an impulse, J, of 7.04. And we can write those units as either newtons times seconds, or equivalently we could say kilogram meters per second. So let's back up now and look at part D. How much mechanical energy was converted to heat and or sound during the collision? Justify your answer. Again, let's go here to some blank space. Let's clear up the last problem for a second. So we want to know how much kinetic energy was lost essentially to heat or sound. So first of all, we need to know how much kinetic energy we started with. Remember that kinetic energy is equal to 1/2 mv squared. At the beginning of the problem, the larger object wasn't moving. The 0.850 kilogram object wasn't moving, so it didn't have any kinetic energy. All of the initial kinetic energy, we'll write it as Ki, came from the 0.6 kilogram object. And it was moving initially at 20 meters per second. We need to square that. Solve that out. And we ended up with having 120 joules of kinetic energy at the beginning of the problem. Now we need to know the final kinetic energy. Well, that's going to be equal to 1/2. Remember that our two carts stuck together. Their combined mass was 1.45. And they moved off with a speed of 8.28. Solve that out. And we ended up with a final kinetic energy of 49.7 joules. Well, this problem asks us how much was lost to heat or sound. So let's just take the 120 that we started with and subtract from it the 49.7 joules that we ended up with to give us a total amount of lost energy. 70.3 joules of kinetic energy was converted to either heat or sound or some other form of energy. Finally, let's look at part E. Calculate the velocity of the center of mass of the two-cart system before the collision occurred. Describe the process logic that you used to reach this conclusion. The center of mass / momentum problems have shown up a lot on the AP exam the last couple of years. What you've got to realize is that during a collision, the mass doesn't change. So the mass before is equal to the mass after. We also know that momentum is conserved. Well, if we thought of the whole object as a point, that point would be the center of mass. So the mass of that center of mass doesn't change before or after. And since the momentum of the system is conserved, that means the velocity of the center of mass also doesn't change. You may have two different parts moving in different directions after a collision, but the velocity of the center of mass doesn't change. So at the end of this problem, the velocity of our center of mass is essentially the velocity of our two objects moving off together, 8.28. That means in the beginning of the problem, the velocity of our center of mass also had to be 8.28 meters per second. All right, that's it. Hope that helps.